Hello students, in the last lecture we left the discussion at the Fraunhofer diffraction at single slit. We already studied that in how many ways Fraunhofer diffraction is different from Fresnel diffraction, and why and how the Fraunhofer diffraction is a limiting case of the Fresnel diffraction. Right, so let's discuss it further. So in this case, Fraunhofer diffraction at a single slit, my source is over here, which is at a focal length of this convex lens. To make the spherical wavefront as a planar wavefront, I use this convex lens. Now the most important condition for the Fraunhofer diffraction is that my source and the screen must be at infinite distance from the obstacle, right? So that's why I use the convex lens over here. So after illuminating a planar wavefront in front of this obstacle is the slit AB. The size of the slit is the of the order of wavelength of this source. So this slit has a very small dimensions. So when I illuminated my planar wavefront on this slit, and when light gets diffracted from this slit, then lights travel. First portion, which is undiffracted rays comes forward and they superimpose at this point P naught, right? And the diffracted rays, we discussed that this is the central maxima, because the rays which are coming from this, or not the rays actually, these are the secondary violet source which are coming forward, does not have any phase difference to each other. That's why they superimpose constructively, and they gave us the maxima position at this point P naught. And now P naught is the central maxima, and it is known as the central because it is at the central distance. Or I can say that when I draw a perpendicular from P naught to this slit, then this perpendicular bisects the slit into portion, right? So that's why this point is known as the central point. And this is a maxima point because undiffracted rays comes over there and they superimpose constructively over there. That's why we get a maxima over here, right? So now for the further discussion, we calculated that if the secondary violet source coming from this point A and the secondary violet source coming from point B, we left our discussion over here. So if this secondary violet source travel further, and they meet at any point P dash or P. Now if they meet at any point P, then if the path difference is equal to n lambda, then we get the minima positions. Now this is the condition for minima. Now it is completely opposite to the interference condition. In interference condition, we got that the path difference must be equal to n lambda. If the path difference is equal to n lambda, then that is the condition for maxima. But not over here. If the path difference is equal to n lambda, we are getting minima at those locations. At these locations, whenever the path difference satisfies the condition n lambda, we are getting the minima positions. And whenever the path difference delta is equal to 2n minus 1 lambda by 2 or 2n plus 1 lambda by 2, we are getting maxima positions. And those maximas are known as secondary maxima. We will discuss that also. So first of all, to understand this thing, the delta is equal to n lambda for minima condition, now we have to study our wavefront. First of all, the wavefront which got illuminated at this slit, we will break that wavefront into two portions to understand this. One portion is from A to this central point and from central point to B. Now all the secondary wave, now consider this, that this wavefront is now broken into two parts. Now first part is completely opposite in phase to the second part. That's why we are getting minima for n lambda, right? Now n lambda means whenever the phase difference between A and B is equal to n lambda, we are getting minima. So we have to take the secondary violet source for minima at the opposite things or with the opposite phase difference. So to consider that, or to get that result experimentally, we need to find out the elementary results as well. So for theoretical explanation, we can take this AB as two portion, and this wavefront is as divided into two portion. A to this central point is a first portion, and the central point to B is a second portion, and both are in opposite phase to each other, and then they travel to this point, and then they meet at this point, and they superimpose in such a manner that they get the minimum position or minimum point with this condition L lambda, right? So that's why. Now how can we break the wavefront into two portion? Like we can consider, like for example, or simply assumptions, if this wavefront has 20 secondary wavelet source, or here I can assume that this is a particle which will travel further, this again a particle will travel further, this again and again, there are 20 particles on this wavefront at the same. Now this wavefront was initially, all these particles were on the same wavefront, means same phase to each other, but now they got diffracted, they have their random orientations, so now they have some phase difference to each other, and that phase difference brings some part difference as well. Okay, so if the first point at A, or the first secondary source at A to on the first part of this wavefront, right, we divided this wavefront into two portion. Okay, so the first particle is just opposite to the first particle of the secondary part of this wavefront. Then the second particle of this first part is just opposite in phase to second particle of the second part. Then the third particle is just opposite to third particle, and fourth particle is just opposite to fourth particle, and fifth particle is just opposite to fifth particle. So both the parts have the particles or the secondary wavelet source which are in opposite phases to each other, right? So this portion, first portion, is just opposite in phase to the second portion. So they will bring this condition that delta, the part difference between them, the first portion and second portion, is just in such a manner that brings the condition N lambda. Okay, so this is all written over here. Now further to discuss this condition, whenever the part difference between secondary waves originating from the corresponding point of wavefront, if this part difference delta is equal to A sin theta. Now we can calculate this. We can draw a perpendicular from this point A on this path traveled by this particle. Then this is the extra path from here to here. This is the extra path, and this path is from geometry we can find out this is equal to A sin theta. Okay, A sin theta. Now A is the opening of the slit, and sin theta is the angle of the diffraction of all the particles. Okay, so this is actually the part difference is equal to A sin theta always. Whenever this point P satisfies the condition of N lambda, you will get the minimum positions, and whenever this point P satisfies the condition of 2n minus 1 lambda by 2, then you will get the maximum position, second to maximum positions. Okay, so now this is for minima, this must be equal to A sin theta must be equal to lambda, or N lambda for first minima. A sin theta is equal to lambda. So we can find the angle of the first minima, that is sin theta 1 is equal to lambda by A. So this is actually sin theta 1, which is actually equal to lambda by A. Now theta is very small, so we can consider that theta is actually lambda by A. Okay, so this is not much of the importance, but we will maybe we need this result in the further discussion. So for nth minima, this is the conditions A sin theta n is equal to N lambda. So you can get the numerical portion from here, that find out the first angle. Now you did this experimentally as well. Okay, we did this particular portion, the Fraunhofer diffraction through the diffraction grating, and we applied this condition that this is equal to 2d sin theta is equal to N lambda for. Okay, so that is diffraction grating portion is something different, but we found out the angle, first angle. Now for the diffraction grating, 2d sin theta is equal to N lambda condition brings the maxima condition, but here this is different. So sin theta for the first minima, we can find out this angle which is equal to lambda by A. So for nth minima, we can find out this is equal to N lambda, and for so on. So for maxima, secondary maxima, a sin theta n is equal to 2n plus 1 lambda by 2, and for different minima and maxima we can find out these angles. Okay, so if I plot the intensity spectra with respect to this a sin theta or the part difference, then whenever the part difference is equal to lambda, 2 lambda, 3 lambda, 4 lambda, I will get the minima positions. Whenever the part difference is equal to 3 lambda by 2, 5 lambda by 2, 4, 7 lambda by 2, I will get the maxima positions. Okay, so in the further discussion we are going to discuss the intensity spectra. And for intensity spectra, now to discuss this theta angle or to find out this theta angle, we hypothetically considered that the this wavefront is divided into two parts, right? And then for the further discussion, I will consider for the intensity spectra, I will consider that there are n particles actually, or I can divide this whole planar wavefront into n strips, n portions, n strips, something like this. Each strips carries one secondary wavelet source, and that secondary wavelet source is a particle. Okay, now these particle came initially with the same phase, but after diffraction they have a corresponding change in phase in the continuous manner. Now the amplitude of these particles remains same actually, but they after diffraction, after striking at this obstacle, they will diffract and they will have a continuous phase change, and that phase change is actually equal to I can find out from this part difference condition. Phase difference is actually equal to 2 pi by lambda into the part difference, so I can find out the phase difference as well. So I will break this wavefront into n strips. Each strips carries one secondary wavelet source, and all the secondary wavelet source has the same amplitude of the oscillation. Okay, so for the further portion we will go discuss that the intensity spectra. Okay.